Hi everyone. So today I'm going to be doing a past paper, a grade 11 past paper, a Department of Education, November 2017, and it's paper 2. So today we're focusing on chemistry. I think it's good for matrics to also go over grade 11 papers because remember, they can still ask you questions from your grade 11 work, right? So it's still very applicable. Okay, so I'm just going to jump straight into it. Question 1, multiple choices, 1.1. Which one of the bonds between the atoms below has the highest polarity? Okay, well, important thing, the way we determine which pairs have the highest polarity is by determining the difference of the electron negativities between the two atoms that are a part of the bond that are under investigation. So we find electron negativity values on our periodic table. We'll find them now. Okay. And what we do is we take electron negativity of atom 1 minus electron negativity of atom 2. You can take the largest electron negativity minus the smallest, and then you get a difference. Okay. And the pair with the largest difference will have the highest polarity. So largest difference in electron negativities means highest polarity. So we go to our periodic table. We find everything we're looking for. So we find hydrogen, carbon, oxygen, nitrogen, and fluorine. Okay, and you can see from the electron negativity readings that they are on the side here. So hydrogen has an electron negativity of 2.1. Carbon is 2.5, nitrogen is 3, oxygen is 3.5, and chlorine is 3. Okay, so we can make hydrogen our smallest electron negativity number in all of them, and we subtract. We say, okay, well, chlorine 3.0 minus 2.1 gives me 0.9. Oxygen 3.5 minus 2.1. You need to grab your calculator and do this little calculation for all of them. So the difference so I think let's maybe write it out. Let me zoom out a bit. And we do like this. So we say 1 is hydrogen and carbon. So you find for carbon, it's 2.5. So it's 2.5. The difference is 2.5 minus 2.1. Electron negativity, you take the largest electron negativity minus the smallest. Hydrogen is always the smallest, so it will always be minus 2.1. So our electron negativity for carbon was 2.5. 2.5 minus 2.1 equals 0.4. Okay, now we do for hydrogen and chlorine. So again, chlorine is 3. So it's going to be 3 minus 2.1, which is going to give me 0.9. Okay, we do number 3, which is hydrogen and oxygen. That's going to be 3.5 minus 2.1. That gives us 1.4. And the last one is hydrogen and nitrogen. And so we go, and nitrogen is 3. So we say 3 minus 2.1 gives me 0.9. And now to determine which one has the highest polarity, we go and we find which one has the largest difference. 0.4 is definitely not the largest. 0.9 is not the largest. Another 0.9, which means this has to be our answer. And our answer of highest polarity goes to hydrogen bonded with oxygen, which is giving me a difference of 1.4. That's my largest difference. So I go back, and what do? I select C. Because C has got the highest electronegativity difference between the two atoms in question, which is synonymous with the highest values of polarity. Okay, moving on. Let's talk about this one. So it says solid iodine sublimes easily. The intermolecular forces present in iodine are. Okay, so let's just talk about the first part here. I just want to quickly remind you of some things. Just to explain what sublimation means, because these are words that could potentially come up and they matter because if you don't know what they mean, you won't be able to answer the question. So, you know that when a solid goes to a liquid, it's called melting. You know that when a liquid goes to a gas, it's called boiling, also known as vaporization. So these are what the phase changes are called. Solid to liquid melting, liquid to gas is boiling or vaporization. Gas to liquid is condensation. Okay. Liquid to solid is freezing. Okay. And then we have what is known as gas. When a gas moves directly to become a solid, it's known as deposition. And when a solid moves directly into gaseous form, it means it's called sublimation. Okay, so you know that when they're talking about sublimes, when solid iodine sublimes, it means that solid iodine is undergoing sublimation and becoming a gas. So it's just important that you remember the names of these changes of state because they definitely could show themselves in your exam. And if you haven't reminded yourself, it might be a bit more challenging for you to answer the question. So I just want to get rid of this so we can have a look at what the question's actually asking us. Because this doesn't really have much to do with the question. Like I said, I just saw the word, didn't want you guys to feel like unsure, especially if it comes up again. But the actual question is saying the intermolecular forces present in iodine are. So one thing that's important to remember is that iodine is a diatomic molecule. That means that when it forms, it can't just form as iodine on its own. It has to form as I2. So one iodine bonded to another iodine. This means that in nature, iodine is never found as just I on its own. It's always found as I2, okay? And if we go and have a look at our periodic table, there are a few molecules that belong to this group, okay? And your diatomic molecules include obviously iodine, bromine, chlorine, nitrogen, oxygen, fluorine, and there should be one more. So our list goes nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and our last one is hydrogen. So these are your diatomic molecules. These are the molecules that always have to be found in nature as H2, N2, O2, F2, Cl2, Br2, I2. They are never found on their own. Okay, so you know that iodine forms part of the diatomic molecules. And now they say, okay, well, what are the intermolecular forces that are present in iodine? So I've got a little summary of our intermolecular forces here. You can see. So dispersion forces are also known as London forces, our London dispersion forces. And these are in all molecules and atoms, okay? Dipole-dipole is between polar molecules. Hydrogen bonding is in molecules that have gotten hydrogen that is bonded to either a fluorine, oxygen, or nitrogen. And ion dipole is when you have an ionic substance and a polar substance and they form bonds, okay? You can also see that there is increasing strength. So dispersion are the weakest, then it's dipole-dipole, then it's hydrogen bonding. Remember, hydrogen bonding is a type of dipole-dipole, but it's a special type that is stronger. And then your ion dipole, which are your strongest forces, okay? So let's have a look. I2, the one thing we can say for sure is that I2 does not have hydrogen bonding because we don't have an hydrogen or an oxygen or a nitrogen or a fluorine. So it's definitely not hydrogen bonding because nowhere in this molecule do we see HNO or F. Okay, the next one is ion dipole forces. Okay, there are no ions here. It's two atoms that are bonded together in the format that they are found in the periodic table. So it's definitely not ion dipole forces. Remember, an ion, if let's say for example we have Cl as it's found on the periodic table, its ionic form. Remember when you learn your charges, the ionic charges, Cl becomes Cl minus. So when they're talking about an ion, they're talking about a atom that is not in, it's not neutrally charged as it's found on the periodic table. It's in its ionic form, which means that it's got a charge. And there's that charge table that you need to study and know off by heart to know which charges they become. Okay, so only if you have an ionic format of a periodic table element do you have potentially ion dipole forces. And then the last one is dipole-dipole. Okay, and dipole-dipole forces are between polar molecules and other polar molecules. Dipole means polar. Okay, and the only way that a molecule can be polar is if it's got an uneven electron distribution. Okay, which means that it's not symmetrical. It doesn't look symmetrical. So if we look at CH4, for example, or methane, CH4 is a symmetrical molecule. Okay, it's got the same atom all the way around it, which means that the electron distribution will be the same the whole way around the molecule. So this is a non-polar molecule and is not considered a dipole. So you'll see this is symmetrical, so it's not polar. But if we have a non-symmetrical molecule, potentially, let's say like water. So water is non-symmetrical because it's got an angular shape, and you can see that there isn't an even distribution of hydrogens all around the molecule. There's a concentration of hydrogens at the bottom, but there isn't hydrogen at the top, which means my electron distribution at the top is not going to be the same as the electron distribution at the bottom, which means it's a polar molecule and it falls under dipole-dipole forces. Okay, now if we compare our asymmetrical dipole or polar molecule, our water molecule, to our iodine, you can see that iodine is perfectly symmetrical. It's got the same atom on the left as it does on the right, and it's a linear shape. It's straight lined. okay? Which means that it cannot be a polar molecule, which means dipole-dipole forces do not apply here, which means the only valid answer we have left is 1.2a. And London forces, as we detected or as we discussed in here, are present in all molecules and atoms. So none of these special or none of these types of bondings which require more specified requirements, none of these kind of fit the bill when we're looking at a double iodine bond. Okay, so the only one that applies is A, London forces. Okay, now we move on to 1.3. The graph below shows how the potential energy varies with distance between the nuclei of two nitrogen atoms when a double bond between the nitrogen atoms is formed. So this is a potential energy graph. We've got potential energy on our y-axis, and we've got the distance between the nuclei in picometers, and this is distance between the nuclei of nitrogen atom number 1 and nitrogen atom number 2. And they're asking you to deduce from the table what is the bond length and what is the bond energy. So I have included a table here of what these graphs are supposed to look like so that you can more easily kind of identify the values that you need to get off of here, right? So you can see this is question 1.3. So you can see we are looking for bond length and bond energy. So we have a look, it says potential energy, increasing destabilization and increasing stabilization as we go down. So you can see here the atoms are at their closest together and repulsion is the strongest force. Okay, and then here at the bottom we have attraction dominates and we have a stable bond formed. Here our atoms are far away and they do not interact with one another. But here we've got our bond length indicated and we've got our bond dissociation energy indicated. So if we're looking for bond length, we're looking for from 0 to the peak of our graph. So from 0 to the peak of our graph, which is 125. Okay, then we're looking for bond dissociation energy, which is from this point up until the peak on the y-axis. So from this point up until the peak on the y-axis, which means our bond energy is 418 kilojoules per mole. So our bond length from 0 to the peak on our x-axis is 125 picometers, and our bond energy, which is from 0 to the peak on our y-axis, is 418. And that corresponds with option C. So C is your answer. Okay, so you see, when you've got this table and you've studied what you need to get off of it, it's quite easy to answer. Okay, now we move on to 1.4. According to Boyle's law, P, or pressure, is directly proportional to 1 over V if T is constant. V is directly proportional to T if P is constant. V is inversely proportional to T. So remember, V is volume, T is temperature, P is pressure. Okay, and remember, if you've written it out like this, you're saying that volume is inversely proportional to temperature because they're not on the same level, they're not in the same part of the fraction. If so look at this. This is the mathematical notation for directly proportional. This is the mathematical notation for inversely proportional. Okay, so if they're in that same place on the fraction, so in the numerator, they're directly. If one is in the numerator and the other is in the denominator, it means that they are inversely proportional. Okay, then we have a look at D. So here D says P, or pressure, is directly proportional to V if N is constant. So I've got a little description here And Boyle's law says that the pressure of a gas increases as its volume decreases, assuming that constant mass and temperature are achieved. So P is directly proportional to 1 over V. Do we have a P is directly proportional to 1 over V if temperature is kept constant? Yes, we do. It's A. Okay? Now we say 1.5. 1 mole of any gas occupies the same volume at the same temperature and pressure. This statement is known as, okay, so guys, you just have to study. This is theory for your gas laws, for chemistry. So if you don't study it, you're not going to know. But if you have a look at my little cue card here for you guys, it says that Avogadro's law says that equal volumes of gases contain equal numbers of molecules in moles at constant temperature and pressure for any gas. And this says 1 mole of any gas occupies the same volume at the same temperature and pressure. So this is in fact 1.5c, Avogadro's law. So you need to go back to your textbooks, and you need to go and refresh yourself on Boyle's law, Charles's law, Gay-Lussac's law, and the ideal gas law. All of them you need to know off by heart. Um, if you don't have this information in your textbook, there is a nice online textbook for physical science. It's for physical science for grade 11 and grade 12. It's called the Siavula Physical Science textbook, and you can download the PDF version of it for free online. You don't have to pay for it. So if you were struggling with these questions because you don't remember these laws and you don't have them in the textbook that you've currently been provided with, you need to go and revise that. And like I said, you can go and use the free online textbook that I've suggested. I use it for my students and it's quite nice. Okay, so 1.6, 1 mole of a gas sealed in a container has a volume V at temperature T and pressure P. If the pressure is increased to 3P, the ratio between the volume and the temperature is. Okay, so it's important to remember that you can use your formulas to kind of get an idea of what the relationship is between these values, right? So they're saying if I increase P, what will the ratio of V to T be if if P is increased by a proportion of 3? Okay. Well, you can see from this formula that P is inversely proportional to V, because you can see V is on the same side of the equation. If we want to see what the relationship is, we have to take V over to this side. And when we take V over to this side, you'll have to manipulate your equation. And this is what it will look like. It will be P is equal to nRT over V. Okay, and remember, if they are on opposite sides of the equal sign in an equation, and one is in the numerator position in a fraction and the other is in the denominator position in a fraction, it means that they are inversely proportional, exactly how I've written it here. Okay, and then according to the same formula, P is directly proportional to T. Okay, so this means that your ratio for P to T is going to be identical. It means that if I increase my P by 3, I'm increasing T by 3 as well because they are directly proportional, which means we need to choose a ratio where T, the number for the ratio of T is 3. So I can cut out this one and I can cut out this one. Okay? So from here, we say to ourselves, okay, well, it obviously means that our correct answer is D. Because you don't usually get values like this in a ratio. When we're working with ratios, we usually try to multiply our ratio by a solid number that will get the ratio in whole numbers. Okay? So it's very unlikely that they'll expect you to answer a ratio in this format, because ratios we tend to prefer to have whole numbers. Okay, we don't leave them as fractions or proportions of a number. So because you've calculated that now t and p will increase by the same value, and you know that fractions and decimals are not usually conventional when it comes to a ratio, you know that you can choose D as your correct answer. Okay, perfect. I just want to get rid of some of this so that we can have a sufficient amount of space to keep answering. Okay, cool. Now 1.7 says that the chemical equation that represents an endothermic reaction is what? Okay, so first thing you need to know is that the change in H, or the change in enthalpy for an endothermic reaction, must always be a positive value. Change in H must always be larger than 0 in an endothermic reaction. So we say, okay, A, change in H is larger than 0, so that is an endothermic reaction. Okay, here we've got change in H is smaller than 0, which means this is an exothermic reaction, because if change in H must be positive for an endothermic reaction, it means that change in H needs to be negative or smaller than 0 for an exothermic reaction. So it's not this one. Then we go to C, and you can see that they've written all of this out, and they've said plus heat on the right-hand side of the equation. Okay, having heat released on the right-hand side of the equation shows you that heat is being released. Okay, if it said plus heat on the left-hand side of the equation, if it said plus heat on the left-hand side of the arrow, that would indicate absorbing energy. And absorbing energy is endothermic, while releasing energy is exothermic. So adding heat on the right-hand side of the equation, or the right-hand side of the arrow of the equation, means that it's exothermic. So it's not this one. If they had said plus heat on the right-hand side of this arrow, it would have been absorbing energy, which would have been endothermic. And for our last one here, you can see your change in H is negative, so it's not this one, which means that the only endothermic reaction present here is A. Okay. Then 1.8, the correct formula for nitric acid. So there should be a list of common names. You should either get it from your teacher, or you need to go online and you need to find it, because they will ask you common names. They can ask you common names. They can ask you common formulas. These are all things you need to know. You need to be able to write down the formula from the common name and the common name from the formula, both ways. You should easily be able to get a table with common names. So, for example, a common name for H2O is water. A common name for there's many common names. Okay, so you just need to go have a look, and you need to know them, and you need to know their formulas. So you will know that if you study, that your formula for nitric acid is HNO3. Perfect. Okay, consider the reaction below. Which substance is the oxidizing agent? Okay, so there's a little formula or a little rhyme that we remember. So this little rhyme goes: oil rig. And what it means is oxidation is the loss of electrons. So basically, becoming more negative. Oh, sorry, more positive. If you're losing electrons, you're becoming more positive. And reduction is the gain of electrons. Reduction is the gain of electrons, which is becoming more negative. Okay, another little rule is that the oxidizing agent undergoes reduction, and the reducing agent undergoes oxidation. So it's opposites. So you need to be very careful. If they ask you which substance undergoes oxidation, then you're just looking for the substance that loses electrons and becomes more positive. Okay? But if they ask you for the reducing agent, if they use the word agent next to either oxidizing or reducing, it means that you are now looking for the opposite of what that word suggests. If the word agent is there, it means you're looking for the opposite of oxidation, of reduction. You're looking for oxidation. If they use the word agent and the word oxidizing comes before it, you're looking for the opposite, which means you're looking for the substance that undergoes reduction and gains electrons. So I know it's a bit confusing, but you just need to read your question carefully. If they ask for the substance that undergoes oxidation, they just use the word oxidation or reduction. It means you're just looking for the thing that undergoes oxidation or reduction. They're asking you in literal terms, they're not trying to confuse you. If they have the word agent there next to either the word oxidizing or reducing, it means the reducing agent is actually the thing that undergoes oxidation, and the oxidizing agent is actually the thing that undergoes reduction. So let's see. They're asking for the oxidizing agent, which means that they're looking for the thing that's undergoing reduction. So they're saying which one is gaining electrons and becoming more negative. Well, let's have a look. So zinc as a solid, okay, starts off with a neutral charge. And on the other side, it's in a bond with ZnSO4. Okay, so now we need to determine what is the charge of zinc on the right-hand side of the equation. Zinc has a neutral charge or no charge on the left-hand side, but we need to determine its charge on the right-hand side so we know, has it lost or has it gained electrons, okay? Well, again, this is where you need to memorize the charges. You should have a charge table where it tells you SO4 becomes 2 minus, Cl becomes 1 minus, OH becomes 1 minus, H becomes 1 positive. There's a list, there's a charge table you should have. I can't stress enough how important this table is. But from that charge table, you should know that SO4 becomes, when it's in its ionic form, becomes SO4 2 minus. And you can see that from the formula here, zinc and SO4 react in a ratio of 1 to 1, which means that we are in fact working with zinc 2 positive. Okay, because why? Because this number, remember when you're naming things, you need your charging, or when you're trying to determine what their formula is and how they react, you take the ion form of one and the ion form of the other, and the charge goes to the bottom of the opposite, and the charge of the other goes to the bottom of the opposite. Now you can see that because there are no subscript numbers here for these atoms or molecules, it means that they are reacting in a ratio of 1 to 1, which means that this -2 and this +2 canceled each other out when they bonded. Okay, which means that zinc, the format of zinc that we're working with is Zn2 positive, which means that zinc with a neutral charge goes to Zn2 positive. Okay, this means that our atom has become more positive. Okay, it's become more positive. Oxidation is the loss of electrons. The only way you become more positive is by losing electrons. And losing electrons is oxidation, which makes zinc our reducing agent. But we're looking for our oxidizing agent, which means that our oxidizing agent needs to be the other ion present in our reaction. It's not zinc, which means it has to be our other ion, which is copper. And we can double check this. We can say, okay, well, copper sulfate, you know the charge of SO4 is 2 minus, which means the copper that we're working with here is Cu2 positive. So it starts as Cu2 positive on the one side, and it becomes Cu solid or Cu neutral on the other side. So that means that copper goes from copper 2 positive to copper, which means that copper is becoming more negative. It used to be positive, now it's neutral, which means it has to have gained electrons. And for it to have gained electrons, it needs to undergo reduction. And the substance that undergoes reduction is known as our oxidizing agent. And it has to be the format of the atom that accepts electrons. So you can't just say copper. You can't just say copper. Because in this chemical reaction, SCU on its own is not the version of copper that accepted electrons. It's not the version of copper that actually underwent reduction. The version of copper that actually undergoes reduction is Cu2 positive because it's this version that then gains 2 electrons to become a neutral Cu solid. So our answer here is B. So Cu2 positive is our oxidizing agent. Okay. Then 1.2, which one of the reactions below will produce the salt sodium ethanoate? Okay, so this may seem like a difficult question, but let's break it down. Sodium ethanoate, you know, O8 is the suffix for carboxylic acids. So guys, remember this is part of organic chemistry. So sodium ethanoate is a carboxylic acid. Okay, so the first thing you know is that your reactants need to have sodium in them. These are your reactants. Your reactants are the things that are on the left-hand side of the equation if the arrow is moving towards the right. Okay, so is there sodium here? No, there's HCl and some type of methanoate, ethanoate. Okay, so it's not A, there's no sodium. Water, and this one, I don't see any sodium here. Okay, now C and D. C and D have got sodium in it. So we've cut down our options. We've gone from having a 25% chance of getting the right answer to now getting a 50% chance of getting the right answer just by eliminating the options that don't have one of the major components in what we're looking for, and that's sodium ethanoate. So now to determine which one it's going to be, and we know it's a carboxylic acid, let's have a look at the functional group of a carboxylic acid. The carboxylic acid, here is what sodium ethanoate looks like. Okay, and a carboxylic acid, as you know, needs to have a double O. It needs to have a double oxygen, one bonded to a carbon with a double bond, and another bonded to an hydrogen to make a hydroxyl group that is bonded with a single bond. So we know to make the carboxylic acid, not only do we need sodium, but we need a COOH functional group. And if we go, only one of the options between C and D has got a COOH functional group, which means that our answer has to be C. Only C is capable of making sodium ethanoate. And I brought this here so that you could have a look at the actual equation when it's complete. So here, CH3COOH, ethanoic acid, plus NaOH, otherwise known as sodium hydroxide, gives us sodium ethanoate plus water. Why? Because the hydrogen from my ethanoic acid is donated because it acts as an acid. And my Na, these split up into Na and OH. My Na then goes and bonds to where the hydrogen left, and the H that left this one goes and bonds to the OH to form water. Okay, hopefully that was helpful. Just might be easier to see the whole equation like this. Okay, now we move on to question 2. So consider the following two reactions of methane. So reaction 1 says CH4 plus HCl gives me CH3Cl plus H2 gas. And reaction 2 says CH4 plus O2 gives me CO2 plus water. So 2.1 says define a covalent bond. So a covalent bond is the sharing of electrons between two atoms to form a molecule. And the other important thing to remember is that covalent bonding happens with nonmetals and other nonmetals. Okay, so that's your official definition for a covalent bond. A covalent bond is the sharing of electrons between two atoms to form a molecule. And then it's just important as a side note to remember that covalent bonds occur between nonmetals and other nonmetals. Okay, so now 2.2 says draw the Lewis structure for CH3Cl and CO2. Okay, so remember the Lewis structure aims to depict all of the valence electrons between the atoms that have bonded with one another. So let's start with 2.2.1 CH3Cl. So you know that carbon is going to be your central atom because carbon is the only one that's capable of forming 4 bonds around it because it's got 4 valence electrons. You can go and you can double check this on your periodic table. Here's carbon. Carbon is in group 14, otherwise known as Roman numeral 4. And this Roman numeral tells you how many valence electrons group 14 has. And so carbon is in this group and it therefore has 4 valence electrons, which means that carbon is the only one capable of forming 4 bonds. Okay, because the others, I think chlorine has got 7 valence electrons, so it's only got space for 1 bond. And hydrogen only has 1 valence electron, which means each of them also only have enough space for 1 bond. So Cl is my central atom, and my other atoms will be H, and now you just go and you draw your electrons. There's a single bond between carbon and all the hydrogens. So you draw little electrons as circles. But you need to remember that you also need to draw the electrons around every single atom. Remember I said hydrogen only has 1, so it bonds with carbon. Hydrogen only has 1, so it bonds with carbon. Hydrogen only has 1, so it bonds with carbon. And chlorine has got 7, so you've only drawn 1. This other electron belongs to carbon. So we go 1, 2, 3, 4, 5, 6. And that's it. That's your Lewis structure for 2.2.1 CH3Cl. Okay? And the next one is carbon dioxide. So it's important, carbon dioxide, again, carbon can make the most bonds around it. So we take that as our central atom. We have oxygen and we have oxygen. Okay? So oxygen has got 6 valence electrons. which means it's got space for 2 bonds. Okay, remember, by the time you've drawn this whole structure out, every single atom also needs to obey the octet rule, which means every single atom needs to have 8 electrons surrounding it. Okay, and the only way that we can achieve this with a carbon dioxide molecule is by establishing double bonds, or by having 4 electrons between 2 atoms instead of just 2. So now with those 4 electrons on this side and these 4 electrons on this side, carbon already has 8 electrons surrounding it, so it doesn't need any more. This oxygen only has 4, this oxygen only has 4. So now we just go and we add another 4 in for each of the oxygens. And that's it. That's your Lewis structure for CO2. CO2 is one of the common ones that you should know has a double bond. The same way you should know that nitrogen has a double bond. Okay, I think let's continue to our next question. Our next question says, how many lone pair electrons are on the central atom in the CO2 molecule? Okay, so a lone pair of electrons is a pair of electrons that is not involved in any bonding. So all 4 of these electrons, or pair 1 and pair 2, are bonding pairs of electrons. These are not lone electrons. Bonding pair, bonding pair. But you can see that this pair and this pair and this pair and this pair, these 4 sets, these 4 sets of 2, or the 2 sets of 2 on each oxygen, are not involved in bonding at all. So these are lone pairs. This is a lone pair, this is a lone pair, this is a lone pair, and this is a lone pair, because they are not involved in bonding. They're just there on their own. So, but they're saying how many lone pairs of electrons are on the central atom in the CO2 molecule. Our central atom is carbon, and every pair, all 4 pairs surrounding carbon, are involved in a bond, which means that there are 0 lone pairs on the central atom. Okay, because all of the pairs of electrons that surround carbon are involved in a bond, which means they are a bonding pair of electrons and not a lone pair of electrons. These are lone pairs, lone pair, lone pair, lone pair, lone pair, because they're not involved in a bond. Okay? So now we move on. 2.4, identify one of the substances in reaction 2 that can form a dative covalent bond when reacting with an acid. Okay, important, a dative covalent bond is a covalent bond between 2 non-metallic atoms where one of the atoms is sharing electrons with another atom, but none of the electrons are theirs. Okay, so for example, I'm going to give you an example of a dative covalent bond. Let's say we have NH3. I just want to go and check how many valence electrons does nitrogen have. Nitrogen is in group 5, which means it has, or it's in group 15, which means according to the Roman numeral, it's got 5 valence electrons. So let's see. 1, 2, 3, 4, 5. Perfect. So nitrogen has a lone pair over here at the top with 2 of its electrons, and the rest of these bonds is formed with 1 electron from nitrogen and 1 electron from hydrogen. Okay, but both of these electrons form a lone pair on the nitrogen, and both of them belong to nitrogen. Date of a covalent bond will be, for example, if you've got NH3 in a reaction vessel with H positive, so a hydrogen ion that's lost its only valence electron. If this hydrogen comes and bonds to this side of this molecule, it forms a dative covalent bond. Why? Because it's sharing electrons. This hydrogen atom is sharing electrons with the nitrogen atom, but both of these electrons belong to nitrogen. This was the lone pair that belonged to nitrogen. This hydrogen molecule doesn't have any electrons to give or to share, but it comes to this NH3 and it says, please, 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 pretty please, will you let me share these electrons with you? And nitrogen says, sure, because if you come and you share these electrons with me, even though they both belong to me, I'll be more stable. As a molecule, I will be more stable. And molecules seek to be more stable, they want stability. Okay, so that's a dative covalent bond. When a atom shares electrons with another atom, but both of the electrons belong to only one of the atoms. So hydrogen has not contributed an electron here. It is just sharing the electrons that actually originally both belonged to nitrogen. Okay? So it says identify one of the substances in this reaction that can form a dative covalent bond. Okay, and one of the molecules that is capable of forming a dative covalent bond, specifically in this group of molecules that they're asking you to choose from here, specifically the answer is H2O. And remember, okay, sorry, my mistake. They were saying just from reaction 2. So just from reaction 2. And I'll show you why water is capable of forming a dative covalent bond. Water has an angular structure. And the oxygen in the center has got a lone pair at the top. Okay? And if we've got a reaction vessel with H2O molecules floating around and H positive ions floating around, as in hydrogens that have already donated the electron to somewhere else, so they're a positive proton floating in our reaction vessel, this hydrogen will also come here and it will say, hey, oxygen, pretty please, can I form a covalent bond with you? Can we please share these electrons, even though they're both yours? And I have nothing to offer in terms of electrons. Please can I come and form a dative covalent bond with you here? And oxygen says, sure, you can share my electrons with me. And oxygen says that because why? Because it makes the molecule more stable. Okay, and this forms H3O positive. So because H2O is capable of sharing its lone pair of electrons that both originally belong to it, because they're capable of sharing these two electrons or this lone pair of electrons with a hydrogen that has no electrons to offer, it is capable of forming a dative covalent bond to give you H3O positive, which is why I said that the substance capable of forming a dative covalent bond is H2O, because H2O accepts an H positive to become H3O positive. Okay, now we go to question 2.5. And question 2.5 says, write down the shape of the H2O molecule and the CO2 molecule. So I just want to, I have a little diagram here to help us. So if you have a look, here's your water molecule, and here is your carbon dioxide molecule. Okay? And they're saying, what is the name of the shape of H2O and CO2? Again, guys, this is study work. I can't really explain this to you. You can't really, in the exam, figure out what these are if you don't know. But H2O is H2O is angular or bent, and CO2 is linear. So this is 2.5.1, it's angular or bent, and this is 2.5.2, linear. Okay, 2.6, although the molecules of CH4 and CH3Cl have the same shape, CH4 is nonpolar while CH3Cl is polar. Give a reason for the difference in molecular polarity. Okay, so again, just want to make some space and I'm going to draw them for you. So CH4, so why is CH4 nonpolar? CH4 is nonpolar because it is symmetrical. And the fact that every single atom surrounding this carbon is identical tells you that the electron distribution all the way around the molecule is even. Okay, now we draw the same thing but with CH3Cl. So remember, one of the key indicators of a polar molecule is the fact that it is asymmetrical. It means that something or for some reason, this molecule is not the same all the way around. Okay, so here you can see the same, the same, the same, the same. It's symmetrical and nonpolar. However, as soon as we swap out one of our H's for a chlorine, which if we go to the periodic table, you can see that chlorine has got a much higher electron negativity. So chlorine has got an electron negativity of 3, and hydrogen has got an electron negativity of 2.1. And remember, electron negativity is the tendency of an atom to attract electrons. So that means that chlorine has got a much stronger ability or tendency to attract electrons than H does, which means that this molecule immediately becomes asymmetrical. This molecule immediately causes an asymmetrical or uneven distribution of electron charge around the entire molecule, simply because this molecule now has a completely different electron negativity to the rest of them that are surrounding my carbon atom. So this Cl makes my molecule asymmetrical and polar. So let's go back and let's just talk about it. You've seen what the structure looks like now. You understand why changing the Cl out from an H makes this molecule asymmetrical, because now it doesn't look the same all the way around and its electron distribution will have changed. So the official answer for 2.6 is the charge distribution in CH3Cl is asymmetrical and CH4 is symmetrical. Okay, the chlorine has a higher electron negativity than hydrogen and therefore results in an uneven electron distribution charge. Okay, so polar, non-polar. I hope that makes sense. Okay, now we move on. Consider the list of 6 substances with their formulae and boiling points in the table below. 3.1. Explain why ethanol is soluble in water. Refer to the relative strength of the intermolecular forces in ethanol and water. Okay, so there is a solubility rule. Okay, So the solubility rule states that like dissolves like, which means that polar substances will dissolve other polar substances, and non-polar substances will dissolve non-polar substances, okay? And then from there, we can just deduce another way to write it in case you're a little bit confused is that polar substances will not dissolve in non-polar substances, and non-polar substances will not dissolve in polar substances. So polar and polar will dissolve, and non-polar will dissolve. This is the rule of solubility. So they're saying to you, okay, well, explain why ethanol is soluble in water. Okay, well, first things first, they've told you that you've got water, which is polar, because you know that the electron distribution is not equal because this oxygen actually has two lone pairs here at the top, which are a lot more negatively charged than your hydrogens at the bottom. So it's a polar molecule. And you know that ethanol is also a polar molecule. And you know that how? You know that because it's asymmetrical. This is what ethanol looks like. It's asymmetrical. If this was an H, if this was just an H and not an OH, it would be perfectly symmetrical because it would have the same distribution all the way around. But because it's got this OH group here that now has a different electron distribution or contributes differently to the distribution of electrons within the molecules, it is asymmetrical and polar. Remember, I told you asymmetrical or asymmetry is a good indicator of polar molecules. Okay, you can also see water is asymmetrical. It doesn't look the same all the way around. Okay, so refer to the relative strength of intermolecular forces. So why will water and ethanol dissolve each other? Why are they soluble? Well, they're soluble, number one, because they're both polar, they're asymmetrical and polar molecules, okay? And additionally, they both have hydrogen bonds. They both have got an oxygen bonded to a hydrogen. Water actually has two. So water has got hydrogen bonds, ethanol has got hydrogen bonds. This means that there is a similarity in the strength of intermolecular forces between them, and therefore they are soluble. So I'll read you the official answer. The official answer says both water and ethanol have hydrogen bonds, which are the same in relative strength. Substances with comparable relative strength and intermolecular forces will dissolve. And that's your answer for 3.1. Okay? 3.2, explain why the boiling point of iodine is higher than that of bromine. Okay? Refer to the intermolecular forces present in each substance in the explanation. Okay? So we're looking for iodine and bromine. So here's iodine. This is boiling point number 1, and this is bromine boiling point number 2. So you can see that bromine has got the lower boiling point, which means it's got weaker intermolecular forces, and iodine has got a stronger boiling point. A higher boiling point, which means it's got stronger intermolecular forces. Okay, so just by looking at the formulas, you can see that both of them should actually be symmetrical, right? So there's pretty much only when this happens and you look at them and you can't immediately identify a difference. The one thing that you need to do is you need to go and check your periodic table, because one of the key indicators of different boiling points is molecule size, molecular mass. okay? And usually molecules with larger molecular masses have got stronger intermolecular forces. So if we go and we have a look, okay, well, here's bromine and here's iodine, okay? This is the approximate relative atomic mass number at the bottom. So you can see bromine has a big M, or a molecular mass number of 80, a relative atomic mass number of 80, while iodine has a relative atomic mass of 127. And there is your smoking gun. There is your answer. The reason that iodine has got a higher boiling point and stronger intermolecular forces is because it has a larger molecular mass. Generally, molecules or atoms with larger relative atomic masses are prone to have stronger intermolecular forces. Okay? So, the question or the answer that's stipulated directly on the memo is the intermolecular forces between the molecules of iodine and bromine are both London forces, otherwise known as van der Waals or dispersion forces, right? Iodine molecules have a bigger molecular mass than the molecules of bromine or iodine molecules. Oh, sorry, yeah. Iodine molecules have a bigger molecular mass than the molecules of bromine, and iodine molecules have a larger surface area than molecules of bromine. And the bigger a molecule is, or the larger its surface area, the stronger its intermolecular forces. Okay? So that's a key indicator for you when you're struggling, when you can't find an exact difference. Always go onto your periodic table and check what the size of the molecules are. Okay, 3.3. Explain why phosphine will evaporate faster than ammonia by referring to the types of intermolecular forces present in each substance. Okay, well, this is our phosphine molecule. Okay, we've got a very low boiling point over here. And this is our ammonia molecule, also very low, but still higher. So they want to know, why will phosphine evaporate faster than ammonia? Okay, well, phosphine will evaporate faster than ammonia because it has a lower boiling point, and a lower boiling point directly translates to weaker intermolecular forces. And when your intermolecular forces are weaker, it means that your molecules are more likely to undergo a transition from liquid to gas. Okay, you don't need as much energy, you don't need as much heat to kind of break the intermolecular forces. So evaporation from liquid to gas occurs much more easily. Okay, and the official answer for this one, it says that the intermolecular forces between phosphine molecules are dipole-dipole forces, otherwise known as van der Waals forces. Okay, and why are they dipole-dipole forces? Well, because NH3 and PH3 are asymmetrical molecules, and asymmetry means that they are polar. So dipole-dipole forces are present. Okay, the intermolecular forces between ammonia molecules are hydrogen bonds. Why? Because in NH3 you've got nitrogen bonded with hydrogen, whereas in PH3, P is not one of the atoms that is on the list that can possibly form hydrogen bonds. But nitrogen definitely is. So NH3 forms hydrogen bonds, which means that it's got stronger intermolecular forces because dipole-dipole forces are weaker than hydrogen bonds, okay? And weaker forces will cause molecules to evaporate faster, or and stronger intermolecular forces will cause your molecules to evaporate slower. Okay, so you might just want to go back, listen to that answer again, write down some of the points we made. Okay, 3.4. Water, ethanol, and bromine are all liquids at room temperature. Which one will have the highest vapor pressure? So it's important to remember that boiling point is inversely proportional to vapor pressure. So that means that the substance with the highest boiling point will have the lowest vapor pressure. So they've asked you to find the highest vapor pressure, which means we are looking for the lowest boiling point. So, but remember, we're looking specifically between water, ethanol, and bromine here. So don't make the mistake of choosing one that isn't in this list of three. So water, ethanol, bromine, which one will have the highest the highest vapor pressure? That's going to be the one with the lowest boiling point, which is going to be bromine. Okay, so bromine. Why? Because it's out of water, ethanol, and bromine. It has the lowest vapor boiling point, and the lowest boiling point is associated with the highest vapor pressure. Okay, 3.4. Give a reason for your answer to 3.4 by referring to the relative strength of intermolecular forces and boiling points. Okay, well, 3.5. The boiling point of bromine is lower than the other two liquids. Therefore, it has weaker intermolecular forces. Okay? If the intermolecular forces are weaker, the vapor pressure will be higher. Okay? Because remember, vapor pressure describes the tendency of a substance to change from a liquid to a gas at that little kind of at that microscopic section between where the top of your liquid reaches the atmosphere. Where your liquid is in contact with the atmosphere, there are constantly molecules changing from gas back into liquid and from liquid back into gas. Okay, and substances that have weaker intermolecular forces will have more molecules that are able to change from liquid into gas into that from that microscopic surface just above where the liquid is. Okay, yeah, so that's the official answer. I think that's good.